Okay, section 1.7 is where we're going to start this whole mess. Everything we're doing up to now has been building up to this. Introduction to proofs, so we're going to do quite a few proofs in here. Now this first paragraph, I got that from the actual book. This is not for this lecture, this is for the next lecture. I'm going to break this into 2 lectures. You know, talk about theorems and propositions and how proofs work. I want to get direct proof out of the way. This is what we're going to do right now. And the first set of few problems. A direct proof of a conditional statement if P then Q is constructed when the first step is the assumption P is true, and you do subsequent steps and construct using some rules of inferences with the final step showing that Q must be also true. A direct proof shows that the conditional statement if P then Q is true by showing P is true, then Q must be true. So it will never be the case that P is true and Q is false. In a direct proof, we assume that P is true and use axioms, definitions, and previously proven theorems together with rules of inferences to show that Q must be true. You will find that direct proofs of many results are quite straightforward, starting with the hypothesis and leading to the conclusion. The way forward is essentially dictated by the premise available at that step. However, direct proofs sometimes require particular insights. We will figure that out in later chapters. For now, we're going to read this definition and make sure we remember it all throughout. If n is even, then I could write n as 2 times k, where k is some integer. So any even number I could write as 2 times an integer. If n is odd, then I could write n as 2k plus 1, where k is an integer. So every integer is either even or odd, and no integer is both even and odd. That's never the case. Any integer you give me, either it's even or odd. 2 integers have the same parity when both are even or both are odd. And they have opposite parity when one is even and one is odd. Alright, well, let's look at page 95 and start with the first proof. It says use a direct proof. We're going to use a direct proof here on these few examples to show that the sum of 2 even integers is even. So if we're talking about even integers, let n and m be even. So let n equal 2k and m equal 2l. If I take the sum n plus m will equal 2k plus 2l. If I factor a 2 out, that's simplification. And since these are integers, because that's an integer and that's an integer, therefore 2 times an integer will show that n plus m is even. Really simple, straightforward. We want to do a couple of those for now, and then we're going to elaborate on rational and irrational in the next lecture. 4 says show that the additive inverse or negative of an even number is an even number. Okay, the additive inverse of x, is negative x. So it's the quantity you add to get a 0. Well, let's say we say m is an even number. The additive inverse of that, this is the sum, is negative 2k, which is negative m. Now, if I take negative 2k, I could say that's 2 times negative k. K is an integer. So since I have 2 times an integer, that is even. And that does the trick. Fairly simple. To show you have an even, you're going to take 2 times an integer. Use direct proof to show that the product of two odd numbers is odd. All right. Let m equal 2k plus 1. That's odd. And let n equal 2l plus 1. That's also odd. So if I take the product, that would be 2k plus 1 times 2l plus 1. That would be 4kl plus 2k plus 2l plus 1. That would be 2 times 2kl plus k plus l plus 1. So if I really think about this, this is odd because I can think of this as integers, but when you add them, you get an integer. 2 times an integer plus 1 is really odd, right? I could say this is 2 into, I don't want to use, I was going to use C. 2 into a plus 1, where a is 2k plus l, 2kl plus k plus l, and that's the form of an odd. So we're not done with this section. This is actually a long section. We're going to stop here for now. I need to practice this a bit before we go on and do the rest.